Now let us continue and talk a bit about image restoration. There are, as we already said, a number of different degradations that we can expect or experience in our acquired images. Instead of having the original image that is not distorted, not degraded in any way, we, due to different imaging conditions, actually get images which are corrupted or degraded by optical blur, so they're over smoothed, or motion blur, which is then blurring some certain direction because someone was moving during the acquisition. Of course, we are discretizing our continuous images of the real world around us. So we have to always have some more or less visible degradation due to spatial discretization, and of course we always have to be aware or count on presence of noise in our system. Then we can model this degradation process, saying that our, let's call it, original image, and that is the ideal one that would perfectly represent the real scene that we are interested in, during the acquisition process is subject to some degradation. This degradation function is, let's say, denoted by H. And after that, there is some added noise to this whole system. And the final output is then denoted by G. So this function G, which is then often called observed image, is what we have to work with. That one is a result of degradation acting on our desired original image, and plus some added noise. Image restoration then aims at inverting this process, undoing it, and aims at starting from this observed image that we have some assumption on how it is created during this degradation process. So the restoration aims at recovering the original image by, let's say, inverting or in some other way undoing the effect of degradation. What we have as a result of restoration is approximation of the original image. Therefore, this hat here in the notation, we call it recovered image. Objective goal of image restoration is then to get the image, to recover the image F hat, which is as similar as possible to the original image F. So as opposed to image enhancement, when we were transforming our images based on some subjective criterion, what we would like to have, for example, a bit smoother image or a bit more enhanced sharp details. Here we are not at all considering what we would like to have in our image. Our objective goal of when doing restoration is to recover the image as it was before the degradation actually happened. So we can say that image restoration then is a collection of techniques that rely on a priori knowledge about the image degradation. So we use what we know about the function H, about the added noise eta. Then attempt is to find a model for this degradation, to actually mathematically express this H and eta, these parameters of the degradation. That may depend on the process, but also the application the concrete image, the concrete data we're working with, the concrete scenes that we're imaging. So all that can be used in order to find a suitable model for the applied degradation. And then the next step is then to use this defined model of the degradation to solve this inverse task, to undo the process of degradation, to recover the image that originally was, was supposed to be the image we are working with. In order to solve this problem, which is, if stated as general as we are stating it here, it is, well, this is quite difficult problem. So in order to solve it, we need to impose some additional constraints. We cannot solve it in this most general case as it is stated here. So the first thing to do is to restrict somewhat the types of degradation that can happen. So we are dealing with a linear degradation model, or we are assuming that the degradation that we can recover or are facing is linear, which will then eventually result in the fact that we can use convolution, which we know is closely related to this linearity, to model our degradation. Finally, methods that we can rely on or will to some extent mention in the lecture belong to two big classes. If we know degradation function, can estimate it quite well, and in case we have a relatively small amount of noise in our images, then we can really solve this inverse task by applying some inverse function of that degradation that we know. That will be then a deterministic process. In the set of other situations where we do not really know degradation function well enough, it's not expressed so that we can invert it and then apply it, and most often have more noise in our images, then we don't really have a chance to follow this deterministic procedure of just inverse process. But then we optimize and we try to, through some stochastic procedure, improve or gradually improve this restored image that should, as well as possible, correspond to the original one. Now, let's see what we can say about degradation model for which we assume is linear and shift invariant. So this is then the expression that we already saw at previous slides. So degradation model with the degradation function acting on the original image with some added noise generates the observed function. Assumptions that we have are on linearity. So this simply says that H is a linear function, and that means that this is its connection and how it acts on a linear combination. We know what linearity means. And then the other one is on shift invariance. So this line here expresses that function H is shift invariant when we have a shift applied, when we apply F to after a shift, then the corresponding shift will actually happen in the response of the function H. So, of course, as already commented, it is not always the case that the degradation we have in reality is linear, and it is not always that it is shift invariant. So these are simplifications that we are using in order to simply derive some theoretical results that can be used to approximate a number of situations, to model a number of relevant situations. Finally, also, we assume additive noise here in this model, where we already commented that noise is not always additive. Sometimes it is multiplicative, depends on the reason and the source of noise, and then most often it is actually mixed. So simply, again, even though this assumed model is not general enough, or let's say it's not general to incorporate all what can happen, we are sticking to it when we derive some theoretical results that can then be useful in a number of situations. So how do we do that? We have this, now we for a while, we don't really, we don't look at noise, we only look at this degradation function. And the first thing we do is that we actually recall that our function can be expressed in the way stated here. So this is often referred to as a definition of a unit impulse. This unit impulse is then denoted by this delta in x minus I. And it may, if we want to find some intuition behind, then we can say that this is essentially intuitively very similar to sampling. So we have function values at some certain points A. We have impulse responses at these locations, and then we are multiplying our function with the impulses, and then integrating over the whole range of, and then that is a way of represent our function f, which we can then use to substitute this expression in this degradation model that we are looking at. So then we have it expressed like this. Now we will apply in 2 steps these assumptions that H is linear, which means that it can commute with integration, which is essentially summation, and that it can also commute with this multiplication with the constant, because this term here, function f, function value at a certain point, is then constant. So we come to this expression due to linearity of function h. Then we have simply introduced some notation for this h acting on a unit impulse here. And we say that that is some function h, which in general depends on x and on the position x and on this value, like location of a shift. So this, which is just 2 names for the same thing, is then, if you look at it a bit better, this is impulse response of this degradation h. It says how, what we will get if this assumed degradation function h is applied to a unit impulse. Okay, so we say that we have this function h that is then this impulse response of the degradation h. Now, using the assumption of shift invariance of h, we can also say that this function here will not just be as general as we stated in the previous slide. Due to this shift invariance, this response will actually correspond to the shift that we have here. So instead of having this general dependence on x and alpha, we will have a dependence of one variable, essentially x minus alpha. This is then what corresponds to what results from the assumption of shift invariance of the function h. Nice. Now, this function here, which we then just use to denote this entity here, is known as point spread function, PSF. It represents a response of a linear system because we use the assumptions that we did, to a unit impulse located at the coordinate x. So this is a unit impulse at the coordinate x, and this is this linear system, model of a linear system. So the response of this linear system, when applied to this to an impulse, to a unit impulse, is then this point spread function. But when we use all this notation and put back in our expression of G, then we get that the following holds. So now we only used what we derived so far on a previous slide, and we come to this expression here. Nice, but we can actually recognize that this expression here is what we know as convolution between these two functions. So another way to write this, which then is our degradation model, is to write it like here. So our observed function, our degraded function G, is then equal to convolution of our original function x and this h, that is point spread function of our linear system. Or expressed as written here, the response to a linear shift invariant, the response of a linear shift invariant system is completely characterized by the convolution of the input system and the system impulse response system's point spread function. Point spread function, response of a system to a unit impulse located at a coordinate x. That essentially means that when we want to model degradation, what we need to know is how that degradation acts to a single impulse. How does the image of a single impulse, how does it look when this imaging system, modeled by now our degradation function, is used? So how does the image of a single unit impulse look? Tells, if we know that, that tells us enough to be able to derive how the whole degraded image will then look. How do we do it? If we know the response to a single impulse, we will apply convolution with our original function, and we will get the degraded, the observed function. Nice. To move from there to actual recovery or to restoration, we will just need to pass through convolution theorem, recalling what we said in the previous lecture. Since now, to undo this convolution will actually be much easier to do in the Fourier domain. So we probably remember quite well that convolution in the spatial domain, corresponds to multiplication in the Fourier domain. And we also know that we have direct or and forward and inverse Fourier transforms to move back and forth from the spatial and Fourier domain, which makes work in the Fourier domain or its relation to the spatial domain quite convenient. Just one comment on the terminology here. So we know now that this function h is then called point spread function. That is, let's say, an image of a single impulse, single bright point in by our imaging system. Its Fourier transform, which appears here, is then called optical transfer function. Optical transfer function, OTF, is something that you might run into, so you should know what it is. In particular, since we're talking about Fourier domain, then the modulus part of the complex function, or which we get in the Fourier domain by Fourier transform, is then called modulation transfer function. So that would be a modulus of optical transfer function being a Fourier transform in itself. Okay, so now we know, now we are thinking in about degradation as convolution, and we would like to undo this convolution. So naturally we are talking about deconvolution, which is also called inverse filtering. Since convolution is essentially filtering, undoing it and doing deconvolution would be quite naturally called inverse filtering. So what are we saying now? Nice, we know that our degradation can, in the Fourier domain, thanks to the convolution theorem, be modeled as this multiplication here. So what we would like then to do is to, knowing this function g, which is the then now Fourier domain, Fourier transform of our degraded observed image, knowing that one, we would like to get this function f, which is then Fourier transform of our original image. And from this expression here, it's quite clear that it's enough to do division of the observed image in Fourier domain and the point spread function in the Fourier domain. And then we are done. Well, it's time to recall or to remember that we did not consider noise so far. So it's time to get it back to the equation. And now when we add noise and also actually work with its Fourier transform, then our algorithm, our formula for recovering our function f looks like this. It has this additional term where we should divide noise in Fourier domain with this same Fourier transform of our point spread function. Looks extremely simple. Let's see what the challenges are. Well, first of all, we need to know this, this function h. So this function h is Fourier transform of our point spread function. Okay, we can say something about how to get to know it, but it's good to be aware that it's not straightforward or ready-made. Another thing that we need to think of is that we are in this formula, actually in both of these, even with no noise at all, we are performing division by h, and that is the division in Fourier domain. And we know how these Fourier spectra usually look and what is the division, how the values are represented there. And then we also know that this division may become division with very small, close to zero values, which are then present in Fourier transform, which will make this division quite unstable, and that can cause problems in this equation. So what we can let's say or respond to, the way we can respond to that to overcome the problem is that maybe not take the whole Fourier, the whole h in Fourier domain, but to actually restrict this observation or the relevant part to only the region where the values in the Fourier domain are reasonably high. So that would be close to origin. So that would be one thing to think about. And finally, for the same reason of non-stable division with h, whenever these values here are small, they will essentially amplify the noise that we have here. So that will that might become a problem to the extent that noise becomes so amplified that it dominates the resulting, let's say, restoration, and we see nothing else but restore noise. These two examples here show what we can do by this inverse filtering, but also how much the result is non-stable, and how much slightly added noise, slightly more noise that is present in this image affects the final result, where in the first case there is some motion blur present here, and there is restoration of the image, which obviously shows some not non-perfect, it's not perfect, but at least we see more than, there are some elements of degradation that are clearly removed. Here we have some noise added, and the result of the same inverse filtering is completely useless, and that is because noise was amplified to the extent that really disturbed the whole process. Okay, but now let's continue with seeing how to solve the first problem listed on the previous slide, and that is, how do we know, how can we learn or conclude or get something about the type of degradation, this H, that we need to divide with, that we can use in this inverse filtering, for example. So one situation is that we have enough of information about the whole the degradation process before we do restoration. So we can derive it either from the known application, from simply knowing the type of degradation that is happening. For example, we know that here we have motion blur, and then knowing that we are dealing with motion blur, then we can maybe from the image that we have from taking some images along the process, having some samples, or knowing something about the motion that was actually happening, we can derive enough of parameters of this motion blur, of this type of degradation, to be able to use it. Or, for example, here, when we know that there is some aerial images, and we know that there is some atmospheric turbulence that acts and blurs our image to some extent, we know that that one is a result of some temperature non-homogeneity that then affects image acquisition process. And knowing maybe the ranges of these temperatures, something more about actual physical and real world situation, we can maybe know enough to derive the parameters of the blur that happens, that affects these images, and then we know more about the degradation process. Knowing simply what caused it, what it is caused by, and also knowing something about actual situation, actual parameters, actual speed of movement, if we deal with the blur, with the motion blur, or actual temperatures and other parameters that cause this atmospheric turbulence. Then we can then incorporate that in the model of our degradation function. Other group of situations is when we do not know enough about, let's say, ideal situation and imaged situation. We do not know how the object looks if not affected by motion blur, and what happens if we have blur. We don't know these details about which would correspond to the speed of the movement and so on. We do not know that how the image should look without, in some other, let's say, atmospheric conditions and so on. We just have the degraded image, and we need to estimate the degradation based on that. So we only have an image, and what we can do, and we need to, and what we can do is then to, let's say, try to figure out from some details in this image how some characteristic features should have looked like without the degradation that happens. So instead of knowing that, as it would be the case in the previous set of let's say, a priori cases of degradation estimate, now we have to know enough about these details to simply know how they would look without degradation. We can often look at some homogeneous regions or at some very characteristic details in some situations, and then simply say, okay, I know that this region should look like whatever, it looks like what I observe, and from these two, I can try to estimate parameters, type and parameters of my degradation. Is it blur? Is it motion? Is it some other type of a problem? We can also say that all what we need to know, based on the theory that we developed, is how is one point imaged by my system. So if I know the response of one impulse, then I know point spread function, and then I know everything I need to know. And that sounds extremely simple, so I should just image a single impulse, single point, and for example, then this would be as an impulse imaged in, let's say, two different systems, I can say, or yeah, and typical appearance of a point spread function where we would say that, and both are some kind of Gaussian responses. And then we would then conclude from there how what is the degradation that we should apply by convolution over the whole image, because that is what was applied to the ideal image, to the original image, to get the observed one that we have. But in principle, it is quite difficult, or it's not at all straightforward. It can be done, but it is not straightforward to estimate the point spread function by imaging an impulse. That is not stable enough. That is rather difficult to work with. There are ways which would then go towards imaging lines instead of points, imaging a set of lines in different rotations, and so on. And by that, essentially getting more stable estimates by then, of course, using these images of lines instead of points by in a suitable way, or rotated lines in like a whole set of such, and suitably then deriving point spread functions in order to get more stable systems and more stable estimate than what it would be if we attempt to image one impulse with our imaging system. Now we know that we can estimate the degradation, so we can estimate our point spread function and go to the Fourier domain and have this function h that we should divide with if we want to perform inverse filtering. But we also know that the direct division with this function h will not really bring very good results due to the problems of division with values that are close to zero. So we might want to improve this direct approach to inverse filtering a bit further by using some knowledge about the actual noise in the image and also defining some criteria that will then set what is that what we actually want to achieve when performing inverse filtering. One way to set such criteria or one such criteria, is quite intuitive one, and in a way already formulated before. That is that we want to have to recover our image so that the recovered version is as close as possible to the original one. And now the question remains, close in what sense? So we can decide or define that what we want to minimize is mean square error, and that is essentially the difference between the restored and the original one squared and summed over the image. This will then be optimality criterion. We would like to solve this optimization problem, but we would like to do that in terms of filtering and in the Fourier domain. So going to the Fourier domain and formulating this same optimization problem suitably in the Fourier domain and solving it analytically, we can derive a filter which can then be used to multiply our observed degraded image and obtain the desired recovered image, which will then, as imposed, be as close as possible to the original one in terms of minimized mean square error. Without going too much into details of the derivation, I will just comment on how this filter looks and what are the components that are incorporated in its formulation. So this is then Wiener filter. And what we see in this formula is, first of all, Fourier transform of the degradation. So we see that this function h, which we worked with and tried to estimate so far, appears here as well. We even see that, so there is some, its conjugate, there is its power spectrum, so square of its modulus, and then there is some additional factor here. So assuming that this additional term is not present, what remains here will reduce to 1 over h. And that means that this would be ordinary inverse filtering as straightforwardly derived as a process to restore our original image. But now we have something here in addition. And the first thing that we can react on or like observe is that having something in addition here will then probably solve our problem of division by small close to zero values, because there will be some additional term, and then we will be safe avoiding these divisions by zero. What is then this term? What does it contain? So there are two things here. One is power spectrum of the noise. The other one is power spectrum of the original image. Power spectrum of the noise is something that we do not always know, but we are kind of used to having this, to the need to estimate it in some way. The problem actually comes with the need to estimate power spectrum of the original image, and that is what in principle we do not know. We do not know original image, otherwise we would not need to restore it. So this ideal Wiener filter, as derived to minimize the optimization function that was defined, has this practical limitation that these two factors are difficult to derive exactly for the given for a given image. To make it practical, this ratio here, this quantity here, is often approximated by a constant value, k, which then simplifies the application, but also goes a bit further from the ideal minimizer that we were looking for. So Wiener filter that is often used in practice then is formulated as this here, where this constant k is approximator of the ratio of the power spectrum of the noise and power spectrum of the original image, which we maybe can estimate in some reasonable way. How does it work? Well, it works actually quite well. So in this example, we are looking at the 3 levels of degradation applied to this original image. So we have blur added, applied to this image, and we have 3 different levels of noise added to the blurred image. This is a very noisy image, then towards the relatively smaller amount of noise added. If we apply inverse filtering in this straightforward, intuitive way, which just includes division by the function h, the result is not very good, and it also clearly depends on the amount of noise that is present in the image. So if we have relatively smaller amount of noise, then by this direct division, we can restore an image that is that somehow indicates how the original image looks, not very closely, but at least there is some content. However, with more noise present in the images, in this image, this inverse direct division, direct approach to inverse filtering does not give any meaningful result. We just amplify the noise that is present in the image. If we use ideal, in this case, Wiener filter, since this is a synthetic example, we can even compute it without this approximation and without this constant k, simply using the exact values that are needed to define it. We have really very much better results. With low amount of noise, we can essentially quite ideally recover the original image. But even in the presence of higher levels of noise, the result looks obviously shows the content of the original image, and is certainly much more successful than the inverse filtering, which was not which suffers from divisions by small values or 0. So now, if you want to apply Wiener filter, then in practice, as we already as commented, we need to set somehow this constant k, and then we can observe in this example how varying k affects the result of application of Wiener filter. So we have some degraded image. We have a detail in this image just for a better visual assessment. This degradation includes certain level of blur and certain level of noise, and then we apply Wiener filter with 3 different values of k, from 10 to the power of -5, -3, and -1. So small, medium, and relatively bigger value of k. And we can then observe the results of Wiener filtering and conclude that, of course, the result is affected by this choice of k. And for very, let's say, for the smallest value of k, we get this image which contains these artifacts that quite clearly do not exist in the original image. If we use a relatively higher parameter k, then we are not removing enough of blur, so this is still quite blurred image. But it is possible to balance this, to find the suitable level of k, so that we actually get quite good result without artifacts and with no undesired blur. So Wiener filter can really produce very good result. However, tuning this value k may be a challenge and certainly has influence on the quality of this result. So let's then summarize what we learned about Wiener filter. And then we can say that this type of inverse filtering, so Wiener filter is a type of inverse filtering with additional information about noise used in the definition of the filter. So it needs to know, it uses information about noise, it uses information about the image, the original image itself, which is the main obstacle to practical application of the ideal Wiener filter. Therefore, it is actually, it reduces to an approximation of the degraded noise, of the degradation. We use, instead of exact values, we use constant k, and that may not be sufficiently good. That certainly brings us further from the ideal optimizer of the criterion that what we wanted to satisfy. And then when we talk about the optimization problem or the criterion that we wanted to satisfy, we should also keep in mind that Wiener filter minimizes mean square error, and that is just one criterion that we can impose when we perform our restoration. But we also know, and we discussed earlier, that mean square error, which is essentially what determines signal to noise ratio as a quality measure for images, is not necessarily perceived as best reflecting the quality assessment by human visual system. So in that sense, Wiener filter will meet the criteria that are imposed, but might not give us results that we will prefer, as we maybe did not prefer images with high peak signal to noise ratio necessarily, compared to, for example, images with high SSIM measure. And finally, Wiener filter will not allow for restoration of spatially varying degradations, which is also one of the limitations of this filter.